Hello. You're probably here because you've been diagnosed with an obstructive lung disease and have been given a bronchodilator to help you breathe. When we breathe air in and out, we have numerous organs and muscles working together with the goal of delivering oxygen to and removing carbon dioxide from our lungs and our blood. This begins with ventilation, in which air enters and leaves the lungs via inspiration and expiration. When we inhale, the volume of the thoracic cavity is increased, causing the outside air to rush into the lungs. When we exhale, the reverse mechanism occurs and air is rapidly forced out of our lungs. The incoming air travels into the nasal passage, down the trachea, and into the primary bronchus, which splits into the left and right bronchi. The bronchi branches into smaller bronchioles, which branch into smaller alveolar ducts, then alveolar sacs, and then finally the smallest alveoli. When oxygen reaches the alveoli, it crosses the respiratory membrane to enter the blood via a process known as gas exchange, where carbon dioxide leaves the blood and oxygen goes in. It is very important that the rate of airflow in the alveoli matches the rate of blood flow in the pulmonary capillaries, so that gas exchange between the two has time to occur. The rate of airflow is inversely proportional to airway resistance, which means that as resistance in the airways increases, airflow decreases. This resistance is controlled via bronchoconstriction and bronchodilation. Our body regulates bronchoconstriction and bronchodilation to ensure that the right amount of airflow is always achieved. So why do you need a bronchodilator, and what is different about your lungs? Bronchodilators are commonly given to individuals with an obstructive lung disease such as asthma. These diseases create more airway resistance than usual due to a narrowing of the airways caused by bronchoconstriction, ultimately resulting in the patient being unable to exhale all of the air from their lungs. Sometimes this airway narrowing is permanent, but often it is reversible and manageable with a bronchodilator. For example, when an individual with asthma is exposed to certain triggers, such as cold air, animal fur, pollen, and exercise, their hypersensitive bronchi will inflame and produce an abnormally high amount of mucus. The individual's airways will therefore be restricted, resulting in a shortness of breath, wheezing, coughing, and tightness in the chest. In order to diagnose someone with an obstructive lung disease such as asthma, we must be able to quantify and measure lung function. This is done by measuring two very important lung volumes: forced vital capacity and forced expiratory volume in 1 second. FVC is the volume of air that an individual can forcibly exhale as rapidly as possible after taking in a deep breath. FEV1 is this same volume, but that can be exhaled in 1 second. We then divide FEV1 by FVC to get a ratio. A healthy individual will have an FEV1 over FVC ratio of at least 70%, which indicates that they can forcibly exhale 70% of their forced vital capacity in 1 second. Any lower than this, and the individual may have an obstructive lung disease. Like its name suggests, a bronchodilator dilates the bronchi, reducing airway resistance and increasing the rate of airflow. It does this by relaxing the smooth muscle of the airways, the airway smooth muscle, also known as the ASM, the muscle that we cannot consciously control. An increased rate of airflow will allow you to expire a healthy amount of air in 1 second, increasing your FEV1 over FVC ratio closer to the normal percentage of 70%. The preferred method of delivery of a bronchodilator is via inhalation, as this minimizes systemic effects and allows a fast uptake into the body. Albuterol, also known as salbutamol and marketed as Ventolin, is one of the most common, and to use it you simply give it a shake, exhale, then inhale deeply while pressing down the button on the top to release a puff of albuterol into your lungs. There are currently 3 major classes of bronchodilators: beta-2 adrenergic receptor agonists, muscarinic receptor antagonists, and xanthine derivatives, each of which target a different pathway in the body to achieve the effect of bronchodilation. To understand how these 3 classes work, it is important to remember that an agonist is a chemical that binds to a receptor to initiate a physiological response, whereas an antagonist is a chemical that binds to a receptor to prevent a physiological response. Beta-2 adrenergic receptor agonists, such as albuterol, bind to and activate beta-adrenergic receptors. Beta-adrenergic receptors are a type of G protein-coupled receptor and are located in both the heart, in the form of beta-1 adrenergic receptors, and in the bronchioles of the lungs, in the form of beta-2 adrenergic receptors. Beta-2 adrenergic receptor agonists are highly important because they have the unique property of binding to beta-2 adrenergic receptors and resulting in bronchodilation, regardless of the constrictor stimuli. This means that it doesn't matter if your asthma is caused by exercise or pollen. Beta-2 adrenergic receptor agonists will relax your airway smooth muscle and help you to breathe normally. Moreover, regular daily use of beta-2 adrenergic receptor agonists will neither improve or decrease your relief compared to as-needed use. This means that it does not matter if you use your puffer on a strict schedule or sporadically whenever you require, you will have relief. The history of beta-adrenergic receptor agonists begins over 2,000 years ago with ephedrine, when it was extracted from the plant Ephedra equiseta in traditional Chinese medicine and used to treat respiratory symptoms in the short term. By the 1900s, epinephrine had been discovered and isolated by an American physiological chemist. Then comes isoproterenol in the 1940s and metoprolol in the 1960s. Unfortunately, while all of these agonists were effective in bronchodilation, they were non-selective, meaning that they target the beta-adrenergic receptors in both the lungs and the heart. This caused hypertension and tachycardia and predisposed patients to cardiac arrhythmias. In 1972, a British pharmacologist discovered albuterol, which is selective for only beta-2 adrenergic receptors in the lungs, and this soon became the leading beta-2 adrenergic receptor agonist. While these agonists are much more selective today than they were decades ago, there is still some controversy surrounding undesired cardiac side effects and mortality. However, it is unsure if this is due to an increased use of beta-2 adrenergic receptor agonists or simply the nature of respiratory diseases. Muscarinic receptor antagonists, such as ipratropium bromide, bind to muscarinic receptors, which are a type of G-protein coupled receptor, which bind acetylcholine, a chemical message used to communicate between the brain and the body. These receptors are innervated by the parasympathetic nervous system, the nervous system which is responsible for rest and digestion. This means that when activated, the parasympathetic nervous system decreases respiration and heart rate and increases digestion. There are 5 different muscarinic receptors in the lungs, 3 of which have a functional role in bronchoconstriction. Muscarinic receptor antagonists therefore block these receptors, which results in bronchodilation, as they are unable to constrict. A side effect of this is mydriasis, increased heart rate, and secretion inhibition. The history of muscarinic receptor antagonists dates back centuries, being initially used in the 17th century as an asthma treatment, often in the form of smoking plant alkaloids such as belladonna, as belladonna contains atropine, which is a chemical capable of bronchodilation. However, in its natural form, atropine can cross the blood-brain barrier, leading to tachycardia. Consequently, multiple chemical modifications of atropine were created, such as ipratropium bromide and oxytropium bromide, which are all incapable of crossing the blood-brain barrier. Unfortunately, these drugs are still thought to contain a slight risk of cardiac effects, similarly to beta-2 adrenergic receptor agonists, but these mainly occur in predisposed patients. Today, muscarinic receptor antagonists are considered widely tolerated. Finally, we have xanthine derivatives, such as theophylline, which are effective bronchoprotective agents. They do this by antagonizing adenosine receptors. Adenosine receptors cannot distinguish between adenosine, a central nervous system depressant, and a xanthine derivative, which allows the xanthine derivative to bind to the receptor, blocking adenosine. This results in nerve cell activity speeding up. This heightened activity causes the adrenal glands to produce adrenaline, which opens the airways as the body believes it is entering flight or fight mode. Ultimately, this results in the relaxation of the airway smooth muscle. The history of xanthine derivatives begins in 1959, when an English scientist stated that one of the commonest and best reputed remedies of asthma is strong coffee. This statement was later explained as coffee, tea, and chocolate all contain methylxanthine, which is a xanthine derivative. After decades of use as a diuretic and a cardiotonic, xanthine derivatives, the most common being theophylline, began to be used as bronchodilators. The downside to this is that patients can have side effects including increased urination due to the mild diuretic properties and a lightheadedness due to the cardiotonic properties of the drug. Also, the most common xanthine derivative, theophylline, has a narrow therapeutic index, which means that a dose even slightly too high can cause serious toxicity. Thank you for tuning in, and I hope that you now have a lot more information about your new bronchodilator.